Morning everyone, my name is Ahmad HAJJAR and I'm Senior Research Associate at the University of Bristol in the UK. Today I'm excited to talk about Robocon tool, which is a new robotic TZ module aiming for in-situ cyclic soil characterization. I will start by showing the problem and motivation and then explaining what is a Robocon tool, and later we'll dive inside the three main components of the Robocon, which are the horizontal PY module, the vertical TZ module, and the torsional tau theta module, and we'll finish by the deployment in situ and the conclusions and next steps. So to frame this presentation, it's important to recognize the broader context motivating this work. And as you know all, now the offshore wind sector is growing rapidly, and it's expected to exceed 800 gigawatt by 2050. And also, the offshore wind turbines are moving to deeper water and more complex seabed conditions. And for the season, we need today an improved and advanced site investigation tool is essential to speed up the pre-construction stage for offshore foundations. For this reason, by using the Robocon, we can skip 3 time-consuming phases in the pre-construction stage. So our contribution is presenting an advanced tool called the Robocon, which is designed to replicate realistic stress paths and generate input for PY, tau theta, and TZ curves used in foundation design. So what is a Robocon tool? It's a new site investigation tool currently under development as part of a multi-institutional UK-Ireland research project. That's an intelligent robotic tool which, upon insertion within the ground, can mimic the loading histories experienced by soil elements around geotechnical infrastructure. So the first section of the Robocon is the PY module, which is doing a horizontal motion similar to those experienced by a laterally loaded foundation. The second one is the tau theta module, which is doing a circular motion in the soil. And the third one is a TZ module doing a vertical motion in the soil similar to those experienced by a pile jacket foundation. So by applying monotony and cycling, we can apply simple and complex loading, replicating the stress and the strain paths experienced by soil elements over entire structure lifetime to support the whole life design approach. So the Robocon project is a collaboration between the University of Bristol, where we are working on the mechanical design, the manufacture, and the initial testing in a small calibration chamber, the University of Southampton, when they are working on the interpretation methods of numerical modeling, and the Trinity College of Dublin, where they are working on the large and in-situ testing in addition to DM calculations. So now let's dive inside the primary module we worked on it so far, which is the horizontal PY module. So we know is a famous existing tools. The CPT is doing a vertical driving in the soil, the pressure meter is doing a symmetrical expansion, and the flood dilatometer is doing an asymmetric expansion in the soil. But as you can see, none of these existing tools can closely mimic the lateral effect of the laterally loaded piles. For this reason, we developed the PY module, which is doing a straight horizontal motion in asymmetric way, different to those experienced by the pressure meter and the flood dilatometer. Here is a photo of the last version of the PY module. It's a cone having 54 millimeter, 10 to 20 millimeter more than the standard CPT, because it's aimed to be inserted after the CPT, and by analyzing the results, we can get directly the PY curve and a few fundamental soil parameters. Here is a photo of the small calibration chamber at the University of Bristol. So we did few tests at a relative density of 20%, we can see how we can, it's evaluating by increasing the vertical stress. And for the same vertical stress, we tried also different relative density. So we can see how the Robocon can apply different loading, and we can see how the response is changing when we are changing the density of the soil, and also we can see how we can keep the loading, the load constant before doing the cycles to dissipate the horizontal displacement, and then we can do elastic unloading and loading to get the stiffness. Now let's go quickly to the second torsional tau theta module, which is still under development. This module is doing a circular motion in the soil. You can see here a photo of the 3D printed version and a typical obtained tau theta curve. So you can see in this video how we can apply an infinite and cyclic rotation of the sleeve, mobilizing shearing along a soil structure interface. Now let's go to the main module of this presentation, which is the TZ module, doing a vertical motion in the soil to estimate the friction, the shear friction in the soil. So in the first version, we tried a single sleeve to investigate the mechanical development, the motor capacity, and the efficiency of the sealing. But obviously, we can see how here the bearing capacity is affecting the results. So we moved to a second version. We split the sleeve in two disconnected sections, and we stringaged the bar. And by using the subtraction method, we can get directly the shear on the sleeve. So we use the same calibration chamber to do testing, and here we use a soil pressure to measure directly the expected horizontal stress. So here we can see a typical shear stress displacement TZ curves resulting from the Robocon TZ module. And by doing a comparison between the experimental results and an analytical prediction based on normal stress applied to the module's interface, we can see a good agreement between the shear strength representing the first cycle of each testing and the Moore-Coulomb failure criterion. In the next steps, we are looking to divide the shell into 3 disconnected sections and install strain gauges here on this bar, on the intermediate section, to estimate the normal stress directly between the soil and the TZ module during the testing, to see what is happening in the cycle and the degradation effect from cycle to cycle, and the difference between the upward and downward shear. In the deployment in situ, we did the first deployment test in the soft pit, which is a big chamber having 5 by 6 meters and a depth of 4 meters. We use the soft sands, and fortunately, by using the hydraulic machine, our Robocon, our aluminum version of the Robocon, was able to support 6-ton driving force, and now we move it to the steel version, which should support much higher. And as you can see, we obtained a typical PY curves showing trends in curve and varying as expected with the depths. In the next deployment testing, as we are working together with Trinity College of Dublin and the University of Southampton, so we are looking to do large calibration chamber testing and in-situ testing in the Kilmac Ridge pile site to validate at a greater scale, in addition to numerical validation of Robocon results at the University of Southampton. So to conclude, we can see that the Robocon, it's a tool still under development, and the early lab validation results are promising. We can see the prototype performance of the PY and the TZ curves resulting from the Robocon. And we are looking ahead in the next steps to further large-scale testing, the installation of pore water pressure and the inclinometer. And in the TZ, we are looking to directly measure the normal stress applied during the testing. At the end, I'd like to acknowledge the whole Robocon team at the University of Bristol, University of Southampton, and Trinity College of Dublin. Thank you for your attention.